This is work I've been doing at NYU at the Courant Institute, mostly with Brennan Sprinkle, Alex Donev, Alice Thornywork, and Alice is, Brennan and Alex are both at NYU, and Alex is in Cambridge, so you might know her. Okay, so let's start by something that I desperately need right now and that I'm drinking right at the moment, which is coffee. So every once in a while, it happens that we take a spoonful of sugar and stir the sugar inside the coffee. Well, at the scales that I'm interested in, which are the nano to micro scales, there's no such thing as a nanoscale spoon. And artificial systems or biological systems have to rely on alternative strategies to perform complex tasks such as mixing, stirring, separating specific molecules, and so on and so forth. And there's one thing that I find fascinating and that also distinguishes these microscales from the macroscopic scales, and those are fluctuations. So if I were to actually have a nanoscale picture of a coffee cup, it would actually look pretty blurry. Okay, now I'm sorry, I jumped a little bit ahead, but so the things that I'm interested in and that I've been interested in for the past, say, 5 years is how we can investigate these fluctuations at the microscopic scale to harness them and achieve complex transports at the macroscopic scale. So I've been investigating 3 different areas, and I'd like to mention all 3 of them, and I'll focus on one main area today. One of them is if you have a complex particle, and those are particles like fluctuating sticky feet that I call fluctuating sticky feet particles, and I'll just say what they are in a moment, they can achieve specific transport mediated by their physical properties. So these particles have a bunch of ligands that jiggle around, that bind and unbind pretty fast on and off to specific receptors on surfaces. And by this binding and unbinding motion, they achieve either directed or non-directed transport that really depends on the properties of the stickers. So I've been doing a lot of work on this. This is related to DNA-coded colloids, if that rings a bell. And if you want to talk more about that, I'd be more than happy to talk about that at some other time. Okay, now the other idea is either your particle is complicated or your environment is interesting. Now, in nanoscale pores, we expect that because confinement starts to be really, really small, whatever happens to the surfaces will impact transport within the interval much, much more than if you're at larger scales. So typically, if you think of a tube, then the jiggling of the tube will affect the transport within the tube. So this is something I've been studying for a while. And now the final thing is, if you look at very small confinements, there's only a few molecules in your confined area at a time. And hence you get fluctuations of the number of particles that affect transport within the pore as well. So I'll be focusing on this today. Okay, so to be a bit more specific and give a concrete example, let me show you a picture of a molecular dynamics simulation of the potassium channel KCSA. Now this channel is a very important channel in our body. Here, the channel is represented by these white ribbons that represent the protein structure. And then there's a small confinement in the middle where you can see purple balls. Those are the potassium ions going through. And then all the rest of the molecules, which are red, represent water molecules. Now, if we run the movie of what happens there, so everything is jiggling around, right? So the confinement fluctuates. And then you can see potassium ions going through the constricted area. And sometimes you see 3, sometimes you see 2 ions inside the constriction, sometimes 4. And it really oscillates between 3, 2, and 4. So it's really not a constant number. And the fact that it's not a constant number really impacts the current that we see going through the pore. So if we do an experiment, and if we apply a voltage bias between 2 sides of this biological pore, but the same goes for a great number of biological porins, but also for artificial pores. So if I apply a voltage drop and I measure now the current going through the pore, the measurement that I will have is something like constant average value, but a lot of fluctuations about that average value. And the fluctuations are pretty strong. And here you see about something like 30% fluctuations. Okay, now, if I go a little bit deeper in these large fluctuations, I can try and analyze them. And analyzing them, one common thing to do is to take the spectrum of this current in the frequency space. And if I plot the spectrum versus frequency, there's some really key features that pop out in these channels. And that is a decay of the spectrum. So I'll zoom in onto it. And the decay decays as 1/f to the power alpha, where alpha is some power. And according to the specifics of the pore, this power changes, but also the prefactor in front changes as well. Now, the thing is, we don't really have a great understanding of how this power, how to describe the prefactor and the power of the decay according to the specifics of the pore itself. Now, it would really be interesting to have that because you have this decay as 1/f, this means that when you integrate back the spectrum, you get a lot of fluctuations and important fluctuations. And in general, we're not really keen on having fluctuations. The first reason being, when I want to make a measurement for a nanoscale pore, I want to be really precise. So typically, if I want to do an experiment through a nanopore where I want to know exactly what is going through, for example, in all sensing applications, such as DNA sequencing, if I take my DNA strand through the pore and I want to know which nucleotide, how the nucleotides are aligned with each other, I pass the DNA through the pore and then I measure the current going through the pore, and the current is blocked when a specific nucleotide goes in. And according to the value of the current that I measure, I can infer whether it's a T, an A, or G base, and so on. But the problem is, since I have these large fluctuations, I'm going to make errors on my reading. So I really want to decrease the fluctuations if I can. So fluctuations in nanopores are a problem, but they're also really interesting and a potential solution to understanding what is going on in there. For example, there are measurements that show that you can track individual reactions taking place inside nanoscale confinement based on these fluctuating spectra. Okay, so I really wanted to understand more about this. And I said, okay, I want to find ways to get some rational information on the signal to noise ratio of current going through a pore. Now, to investigate this question, because it's a really, really broad question, so you have many kinds of pores, artificial or bio, you have different kind of molecules permeating through these pores, I started with the traditional mathematical or physical approach, which is to say, let me take the simplest system possible and understand what I can from there and then build on that. So I started with a membrane that has a circular pore of radius r that is dividing a space of two reservoirs, one on the left and on the right. And then permeating through this pore are a bunch of molecules here depicted by these red balls. And basically these particles are the simplest particles there can be. They are brownian and uncorrelated, meaning they represent typically diffusive molecules that don't interact with each other. So they're not even ions, right? They're just simple particles. Now this seems like a very simple problem, but already here, something that is tricky to tackle is the fact that you have reservoirs and a pore, so a specific geometry at play. And in fact, what this system is doing and why it's interesting to study this system is to probe the effect of reservoirs on passage of ions through, of particles through the pore. Okay, now what can I measure in this system? The simplest thing that I wanted to measure was the difference between the number of particles to the right versus to the left. So number of particles in the right reservoirs versus to the left reservoir. And this is an interesting quantity because if I take its derivative, this is measuring the current. And this is all done at equilibrium. So for now, there's no actual driving. You're measuring around the equilibrium. But one could imagine putting a field that drives the particles, the red particles through, and then looking at different features on delta n, for example. But we start at equilibrium. Okay, now, as I said, this is already a complicated problem to look at least analytically. So I started by doing simulations and said, well, I'm going to investigate this delta n and see what happens. And so in average, if you look at delta n, well, in average it's 0 because the reservoirs have the same size. So number of particles on the right equals numbers of particles on the left. Okay, and then it's a fluctuating signal because particles move backwards and forwards. And so I can investigate something on this delta n. It's not the average of delta n over noise, but it's the mean square displacement of this quantity. So delta n squared, averaged over noise, versus time. So here I'm measuring exactly the mean square displacement of this quantity delta n. Okay, now here I'm plotting it for different values of the pore radius r. So for small pores in orange, I find that the number difference grows linearly in time, and that's a diffusive noise, and that's kind of expected because I had diffusing walkers, so I expected diffusion for any kind of quantity I was going to measure. And then when I increase the size of the pore, at some point, I see other features pop up, and importantly, I see a square root of time dependence of this number difference squared. So this is a subdiffusive kind of noise, and if we're more specific on the exact kind of noise that it is, it's actually a fractional noise. But the most important point here is that I was really surprised to see a subdiffusive component on such a simple diffusive system that was really uncorrelated walkers, but in a specific geometry. So the reason for this subdiffusive noise actually inherits from a property of Brownian motion that I'm going to walk you through right now, and that I find fascinating. So here we see that this subdiffusive component arises when the radius of the pore is quite large. Now, the extreme limit of that is I have an infinite pore radius. So in fact, I have no membrane. And if I have no membrane, everything is equivalent as if I were looking at walkers on a line. So now I just have walkers on a line, and I have this imaginary membrane in the middle dividing the left and right space where I measured delta n. Now that everything is on a line, it's perfectly feasible to analytically define what delta n should look like. Since I have n uncorrelated walkers, I can just focus on one and say I focus on one that started on the left-hand side its walk. If it passes on the right-hand side at some time t, then it will change delta n by a factor +2. So if I measure delta n squared, the quantity of interest, it will be equal to 2 to the squared times the probability that my walker started anywhere on the left and made it to the right. Now, since my walker can go from left to right, but also the reverse way, I also have to multiply by 2. Now, what is this probability? This probability is I started anywhere on the left. So if I focus on my particle that started anywhere on the left, its probability distribution function is a step. Is a step. Okay, and then as time evolves, my particle diffuses, and so it's the probability to find it will smear out. And the way it smears out is given by an analytic expression based on the error function. Now, after some time t, the probability that my particle went to the right is just the integral under the probability distribution. And so it's this white triangle. And if I make this integral, I find that the probability to go from the left-hand side to the right-hand side after some time t scales as square root of time. So it's this simple math property. Now, wrapping all things together, I obtain that delta n squared is equal to some prefactors that I won't discuss times square root of time. So what does that mean? Well, I started from a simple Bronin-Walker on a line, and I found that looking at this quantity delta n builds up a quantity that has a fractional noise in time. Okay, and so I find that beautiful per se as a mathematical property. But what's interesting is that here I took a specific thing, which was delta n, number difference between the right and the left. But actually, I could have taken any kind of other region of space. So say a box in the middle, a long box, a short box, two boxes, and measured how many particles were in that box, or other kinds of operators that were differences of numbers. And counting numbers in regions from a random walk basically gives a fractional noise in time. So whatever kind of thing that I look at, which is defined on a region of space for Bronin walkers, will give this fractional dependence on time. Okay, so that was Bronin motion. Now going back to the actual system of the 3D pore, well, why do I see this happening for 3D pores and not for all kinds of radii? When I look at this more complex system with reservoirs, it's not possible anymore to do the reasoning that I did before on the line. So one has to come up with other ideas. And the idea that I came up with is to reduce this complicated geometry to a simpler geometry. Here, if you focus on this pore, there's actually two kinds of particles, those that are in front of the pore and that can make it through if they just go straight, and those that are not and that will rebound on the membrane. This maps up to two lines, one line that is passing in blue and one line that is blocked in gray. And because, of course, particles can move from one line to another, I have to define rates going from one line to another, say Q on to the passing line and Q off out of the passing line. And the rates are given by the ratios of the areas of open pore and closed pore, or enclosed surface, that scales typically as the radius of the pore squared. And they're given by this surface area to be in accordance with detailed balance in the global system. Now this mapping is actually reproduces the simulation data. So it's a very good idea to map the system on the simpler geometry. And the cool thing about this mapping on lines is that I can use the artillery of analytical solutions and so on to find results and systematically investigate lots and lots of systems. So that was cool. And I'll bring you through what I learned. Okay, so if I remember again that I had different behavior according to the radius of the pore, now actually the story is not so much about the pore radius, but about time. So looking at this delta n squared difference in time, but enlarging the y-axis of time, I find that at very early times, I get a subdiffusive component that corresponds to particles that were very close to the pore and that don't come from very, very far away. So time is not large yet. So those particles that come from very nearby, well, they didn't have time to see the membrane. They just see an open space. So in fact, everything happens as if my membrane was wide open. And then as time goes by, particles that make it through the pore come from further away. And those have to find, rebound on the membrane and have to find this open area. So this is a diffusion limited regime. And then at larger times even, particles have basically averaged out over all this geometry and only see in average an open pore. So you get these three regimes, and the interplay between one and the other, of course, is controlled by the radius of the pore. So if I go back to my system of, to this initial plot, well, basically, as I was focusing on a narrower window of time, one of them was not limited by the time to reach the pore, but was basically probing particles nearby the pore, so the large ones. the large pores, sorry. And then the other one was diffusion limited, and that corresponded to the regime of finding the pore because the pore was narrower. Okay, going back to my initial question, well, now that I have this delta n squared in time, I can plot the frequency spectrum, and I find that subdiffusive motion yields 1 over f to the power 3/2 dependencies in the spectrum, and diffusive leads to 1 over f to the power squared. So I get these 1 over f to the power alpha dependencies. I can analyze them, I can have their amplitude, etc., and decide what kind of radius to take to minimize the amplitude of the noise. But more to what the outcome of this is. So first of all, this is applicable to many different kinds of systems. I showed you this open pore, but you can think about lots of different geometries and probe, for example, the number of particles within a thick pore. And you would also get 1 over f to the power 3/2 dependencies. Okay, and skipping on, these dependencies as 1 over f to the power 3/2, so corresponding to subdiffusive noise, I have seen them in many, many works, and here I show two, one experimental work and one advanced numerical work, where the power 1 over f to the power 3/2 pops up pretty often. So I think this is due to this intrinsic property of Brownian motion. And to demonstrate this with Alice, we have a really nice and simple experiment. So Alice has colloids in water, and the colloids are pretty heavy. So they're basically lying in 2D, and they're jiggling around. Okay, and something easy we can do with these experiments is to decide on a region of space over which to observe these colloids and track the number of particles within that area. So defining a region, calling n the number of particles within that region. And then in average, there's an average number of colloids corresponding to the density of colloids. And then I can probe the mean square displacement of n with time. And here I can do that for different boxes and so on, but I really find this subdiffusive behavior in time that demonstrates the sort of universality of this subdiffusive motion, so this fractional motion. And like it fits well with theory. It works well with theory that is not fitted, sorry. Okay, I will stop here, conclude. Fractional noise is this intrinsic property of Brownian motion that leaves traces in the noise spectrum, especially as 1 over f to the power 3/2. And that happens in many, many different systems. So I can't wait to see more consequences of this fractional noise behavior. Thank you.